Hi students, in this class we are going to solve a numerical problem on nominal pi method. We have a three-phase transmission line. Its length is 150 km. The resistance is 0.1 ohm per phase per kilometer. The inductive reactance is 0.5 ohm. Capacitive susceptance is 3 into 10 raised to minus 6 Siemens. Susceptance is same as admittance. It is the inverse of reactance. The receiving end power is 50 megawatt at 110 kilovolt. Power factor is 0.8. We need to find out the sending end parameters. These are the load parameters: 50 megawatt. Power factor is 0.8 lagging. Voltage is 110 kV. The resistance of the line is given as 0.1 ohm per phase per kilometer. The total length of the line is 150 km. So it is equal to 15 ohm. So R equals 15 ohm. Inductive reactance equals 0.5 ohm per phase per kilometer into 150 km. It is equal to 75 ohm. The inductive reactance is 75 ohm. Capacitive susceptance is 3 into 10 raised to minus 6 Siemens per phase per kilometer. And the total length is 150 kilometers. So it is 45 into 10 raised to minus 5 Siemens. Half the susceptance is on the left side, half is on the right side. So it is 22.5 into 10 raised to minus 5 on the left side. Here also it is 22.5 into 10 raised to minus 5 Siemens. These are the transmission line parameters. Now we have to find out the receiving end current. Finally, we will find out the sending end parameters. We are going backwards. We start with the receiving end. Step by step, we are going backwards to find out the sending end parameters. The receiving end voltage is 110 kV. The voltage given in the problem is the line value. We assume that it is a star connected system. So line voltage equals root 3 times phase voltage. So the phase voltage at the receiving end equals 110 into 10 raised to 3 divided by root 3. So this is equal to 63508 volt. This is the magnitude of voltage. We have to write all parameters in the vector form, which is equal to 63508 plus J0, because we are taking the receiving end voltage as the reference vector. So it is 63508 plus J0. Now we will find out the receiving end current. So you know P equals root 3 VL IL cos phi. So the line current equals P divided by root 3 into VL into cos phi. It is equal to 50 into 10 raised to 6, because it is 50 megawatt, divided by root 3 into 110 kilovolt. It is 110 kilovolt. 110 into 10 raised to 3 into cos phi is 0.8. So this is equal to 328 amperes. As you know, in the star connected system, the line current is same as phase current. So the receiving end phase current is equal to 328 amperes. It is same as the line current. Now we have to write the current in the vector form. The vector representation, it is magnitude into cos theta plus j sin theta. So here it is cos phi r plus j sin phi r. The power factor is 0.8. From this we can find out phi r. It is equal to 36.86. As it is lagging power factor, you have to give negative sign. So this is equal to 328 into cos minus 36.86 plus j sin minus 36.86. So this is equal to 262.4 minus j 196.8. So this is our receiving end current. It is 262.4 minus j 196.8 amperes. Now we have to find out the current flowing through this capacitor IC1. IC1 is equal to current equals voltage across the capacitor. It is same as the receiving end voltage because capacitor is in parallel with the load, divided by capacitive reactance. It is minus jXC. 1 by minus j is equal to plus j into VR into 1 by reactance equals the admittance. Here it is y by 2. This is equal to j into the receiving end voltage is 63508 plus j0 into y by 2. Y by 2 equals 22.5 into 10 raised to minus 5. So this is equal to J 14.3 amperes. It is J 14.3 amperes. Now we have to find out the line current, which is equal to IC1 plus IR. IL is equal to IR plus IC1. That is equal to 262.4 minus J 196.8 plus IC1. That is J 14.3. So this current equals 262.4 minus J 182.5. So this line current equals 262.4 minus J 182.5. Now we can find out the sending end voltage, which is equal to the receiving end voltage plus the drop. Vs is equal to VR plus IL into Z. So this is equal to VR equals 63508 plus J0 into the line current is 262.4 minus J 182.5 into the impedance. It is 15 plus J 75. So this is equal to 81131.5 plus J 16942.5. This is our sending end voltage. In the R theta form or in the polar form, this is 82881 angle 11.79 degrees. So Vs equals 81131.5 plus J 16942.5. In the polar form, this is 82881 angle 11.79 degrees. So this is our sending end voltage. Now we can find out the sending end current. For that we should know IC2. IC2 is equal to voltage across the capacitor by the reactance, where the voltage is Vs divided by capacitive reactance is minus JXC. It is equal to 1 by minus J equals plus J into Vs into 1 by reactance equals admittance. Here it is Y by 2. So this is equal to J into the sending end voltage. It is 81131.5 plus J 16942.5 into Y by 2. It is 22.5 into 10 raised to minus 5. IC2 equals minus 3.81 plus J 18.25. IC2 equals minus 3.81 plus J 18.25 amperes. This is our capacitor current. Now we can find out the sending end current, because sending end current equals the line current plus capacitor current. IS equals IL plus IC2. So this is equal to IL is 262.4 minus J 182.5 plus IC2 equals minus 3.81 plus J 18.25. This is equal to 258.6 minus J 164.25. This is our source current. In the polar form, this is equal to 306.35 angle minus 32.42. So source current equals 258.6 minus J 164.25. In the polar form, this is equal to 306.35 angle minus 32.42 degrees. Now we got the source current. Now we can easily find out the sending end power factor. Phi s is the angle between Vs and Is. Angle of Vs is 11.79 minus angle of Is is minus 32.42. So this is equal to 44.21 degrees. So sending in power factor cos phi s equals 0.7167 lagging. So cos phi s equals 0.7167 lagging. The receiving end power factor is same as the load power factor, it is 0.8. Now we can find out the regulation, which is equal to sending end voltage minus receiving end voltage divided by the receiving end voltage. If you write the voltages in line values, both Vs and Vr should be line values. If you write them in phase values, both should be phase quantities. Here we can write both Vs and Vr in phase quantities. The same sending end voltage is 82881. You have to write the magnitude only. The receiving end voltage is 63508 divided by 63508. It is equal to 30%. So the regulation is 30%. Now we have to find out the transmission efficiency, which is equal to the receiving end power minus divided by the sending end power. The sending end power can be calculated as 3 into Vs Is cos phi s, 3 times the phase power. It is equal to 3 into Vs equals 82881 into Is equals 306.35 into cos phi s equals 0.7167. So this is equal to 54 megawatt. The receiving end power is 50 megawatt. The transmission efficiency equals output power or the receiving end power divided by the input power or the sending end power. So this is equal to, the receiving end power is 50 megawatt divided by the sending end power is 54 megawatt. So efficiency equals 92.5%.